In this video today, we're going to do a chemical reaction between cobalt chloride hexahydrate, and we have 3 grams of that, and hydrochloric acid, and we have 12 mils of that, and we're going to dilute up to the mark using water. To start this chemical reaction off, I'm going to add my cobalt chloride hexahydrate into our volumetric flask, and I'm just going to wash it down with water. And when I start adding water, you'll see this beautiful red color due to our hexa aqua cobalt 2 ions, which are present in solution, and that gives us an indication of what our starting material's color looks like. And then to finish this chemical reaction, I'm going to add in my hydrochloric acid to this, and when I do that, you see this beautiful blue color due to the presence of our tetrachlorocobaltate ions, our product. And this is an indication of the color of our product here, blue. And what's actually happened is our hexa aqua cobalt 2 ions have reacted with chloride ions to give us this tetrahedral tetrachlorocobaltate ions and water. Now, when we make it up to the mark using water, we start to see something strange happening in the solution. We start seeing the blue color on the bottom and then this red top layer. So the blue color was due to the products being formed, and the red color was due to our reactants in solution. So this isn't behaving as a normal chemical reaction would. We're seeing that we're having both product and reactant in the same vessel here. And this final purplish red color is due to the presence of both our blue tetrachlorocobaltate ions and our red hexa aqua cobalt 2 ions present in solution. So here, something strange is happening with this reaction. It's able to proceed in both the forward and the reverse direction quite happily, depending on the concentration. When we reacted hexa aqua cobalt 2 ions with hydrochloric acid, which yielded chloride ions from HCl, we got tetrachlorocobaltate ions. The only thing was, when we actually increased the amount of water, i.e. we diluted the solution up to the mark in the volumetric flask, we found the color changed from blue, and the blue color was due to the tetrachlorocobaltate ions, to a purple color. This purple color was due to the presence of both the tetrachloro complex and the hexa aqua complex. The hexa aqua complex was giving it a red characteristic, and the tetrachlorocobaltate ions were giving it a blue characteristic, making a purple color. In a normal chemical reaction, what we would expect is that we add our 2 reactants together, and the reaction would proceed to our products. And then there would be no ability to actually back react. This reaction, however, has the ability to go backwards and forwards, which is indicated by this equilibrium arrow here. So this reaction is able to decide what extent of the reaction it is going to proceed to, depending on the concentration of the products and the reactants. So this type of reaction is called an equilibrium reaction. We understand in our everyday lives what equilibrium means. And equilibrium usually means in our everyday lives that there is some kind of a balance. And for a chemical reaction, that balance is the balance between the reactants and the products, or the concentration of the reactants and the products. If we look at the concentration of here hexa aqua cobalt ions as a reaction proceeds, we can see initially the concentration of those is quite high, and they will be consumed as we start producing these tetrachlorocobaltate ions. We say that the reaction has reached an equilibrium when there is no net change in those concentrations. So let's look at that from a different direction, and that is the direction of the reaction rates. So we always say that an equilibrium is dynamic and that it's never a static process, because no matter what point you are in the equilibrium, there's always a forward reaction and a back reaction. And these reactions are often taking place at a very fast rate. And when equilibrium is reached, that balance between the concentration of the reactants and the products is reached, we say that the rate of reaction of the forward reaction and the rate of reaction of the reverse reaction are actually equal. So when the concentration of the reactants is rather high, we'd expect the rate of reaction of the forward reaction to be fairly high. And that rate of reaction of this forward reaction is going to decrease with time as the reaction proceeds. If we have a reversible reaction, like we've seen just before, then our reaction rate of the reverse reaction will start off very slow because we haven't had time to produce our products yet. But then our reverse reaction will speed up because we're getting more and more of that product being formed. At some point, we will have both the forward reaction and the reverse reaction being equal. And this is the equilibrium point. And this is why we always indicate an equilibrium with these arrows here, the forwards and the backwards arrows, because the reaction can proceed in either direction quite happily. If we think about this equation of this forward and backwards reaction, we could probably play around with this. And we probably understand for a single step reaction that the rate of reaction is the product of the two concentrations of those reactants times the reaction rate constant. And here I have Kf because it's the forward reaction. And for the reverse reaction, it's the product of the two concentrations of the products times by the reaction rate constant. And here I've put Kr because it's the reverse reaction. At equilibrium, those two reaction rates are going to be equal. So we can equate those two reaction rates together, and we can get all of the concentrations together and all of the reaction rate constants together. And we then produce something here, which is the ratio of the forwards and the reverse direction. And we call this the equilibrium constant because that's a constant. The reaction rate constant is going to be a constant only depending on the temperature. So therefore, at a single temperature, we can expect these concentrations to always remain in this sort of ratio. To get an equilibrium constant, we need to take a ratio of the concentrations of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. We think about what the equilibrium constant represents, and we think about any reaction as being a transition from reactants to products, then our equilibrium constant is really like just this ratio of our products to our reactants. So this means that our equilibrium constant is always greater than 0 because this equilibrium constant is a ratio of our reaction rate constants forward and backwards. It is a constant at a particular temperature. And if we have a K that's much greater than 1, this means that our products are going to dominate in the reaction. If, however, it's some number between 0 and 1, this means our reactants are probably going to dominate and there's not very much of our products. So this gives us a very quick way of understanding which side of the reaction will proceed to just based upon the equilibrium constant. So for a small K, and I've given the example of nitrogen reacting with oxygen to produce NO, that K is 1 by 10 to the minus 30 at even 1000 Kelvin. This means that there's basically no reaction is actually going to occur. However, if we have a very large K, and here I've given the example of carbon monoxide reacting with oxygen to produce carbon dioxide, that K is going to be 2.2 by 10 to the 22 at 1000 Kelvin. This means that the reaction is going to proceed to completion because of that ratio of products to reactants. Because our K is a very, very large number, This means that there's not going to be very many reactants left. If, however, our K is some number that's close to 1, that means there's going to be a very good balance between the products and the reactants, and there's going to be both products and reactants remaining in a reaction mixture, which really reaches equilibrium. Now, there is all different types of Ks, but all of these Ks are derived exactly the same way. It's always going to be the concentration of our products raised to their stoichiometric powers divided by the concentration of the reactants raised to their stoichiometric coefficient. So there are various types of ones. There's the equilibrium constant based upon concentration units. There's equilibrium constants based upon pressure units. There's solubility products. There's acid and base equilibrium constants. There's stability constants of coordination compounds. There's indicator equilibrium constants, and even partitioning constants in chromatography are based upon the same K. The thing about equilibrium constants, however, is the concentrations of pure solids and pure liquids aren't going to change, although their amounts may change. So these terms, i.e. the concentrations of pure solids and pure liquids in an equilibrium constant aren't there. So we actually exclude those terms. So if we have if we're trying to write the equilibrium constant of this reaction here, the reaction of calcium carbonate to produce calcium oxide and carbon dioxide, we don't include the concentrations of those two solid products there, the calcium carbonate and the calcium oxide. We only include the concentration of the carbon dioxide. So here our Kc is equal to the concentration of the CO2 above the reaction. Or if we were to express that as a Kp based upon pressure units, we'd write the partial pressure of carbon dioxide. If we have hydrogen iodide in the gaseous form reacting to give us hydrogen gas and iodine solid, the iodine solid wouldn't appear in our equilibrium constant, and it would be just the ratio of the hydrogen divided by the concentration of the hydrogen iodide raised to the power of 2. Or in pressure terms, it would be just the partial pressure of hydrogen divided by the partial pressure of the hydrogen iodide raised to the power of 2, because it's the stoichiometric coefficient out the front. K and later on Q are unitless numbers because each term in the equation represents the concentration in standard thermodynamic state. And this standard thermodynamic state is 1 mole per liter. So we ratio it against this thermodynamic state. So if we have a concentration of 1.2 moles per liter, then we divide by that standard thermodynamic state of 1 mole per liter, and that gives us a value of 1.2, not 1.2 moles per liter. So that means that all of our units for concentration in K and Q cancel each other out, and which leaves K and Q as dimensionless numbers. So I've talked just briefly about Q, and Q is a reaction quotient, and this reaction quotient is expressed in exactly the same way as a K, but Q here applies to a reaction prior to it reaching equilibrium. So for a general reaction, A moles of A going to B moles of B, and that goes to C. For the general reaction of A moles of A reacting with B moles of B, which goes to C moles of C and D moles of D, we'd write it in exactly the same way. The concentration of the products raised to their stoichiometric powers divided by the concentration of the reactants raised to their stoichiometric powers. The reaction quotient allows us to predict how a reaction is going to proceed if it's not at equilibrium already. So if Q is equal to K, the equilibrium constant, then we're already at equilibrium. However, if Q is small when we compare it to K, The only way that Q is small compared to K is that top number, the concentrations of the products, is small and the concentration of the reactants is large. That means that the reaction hasn't proceeded to the right enough, so we need to produce more products. So the reaction will naturally proceed towards the product side. That means we can then predict if Q is small compared to K, then our reaction will proceed to the right, to the products. So we can understand how a reaction behaves by looking at its equilibrium constant. So to write an equilibrium constant, we need a balanced chemical reaction. And here we have a balanced chemical reaction. We have a hexa aqua cobalt ion reacting with our chloride ions to form our tetrachlorocobaltate ion and water. And we can see that all of the atoms actually balance up. So to understand this reaction and how it behaves, we need to actually look at the equilibrium constant of this reaction. To write an equilibrium constant, we take the concentration of the products, and here we have our two products here, and we write them down. Now, for water, we don't actually write water down in this reaction, however, because it is a pure liquid here, and pure liquids and pure solids do not appear in equilibrium constant. So we will not write down water for this, but we need to divide through by our concentration of our two reactants here raised to their stoichiometric coefficients. Okay, so here we've got our cobalt complex here raised to the power of 1 because we have a 1 out the front. We have a 1 out here, so because of the 1 out the front of this reaction here. We have a 4 because of our 4 here, okay? So now we have our equilibrium constant. We can understand what's going to happen to reactions when something is changed. And the way that we do that is we write down another number, Q, which is kind of like intimately related to our equilibrium constant. It's a reaction quotient, and it writes down the equilibrium constant for the current conditions, not necessarily equilibrium. So K is for equilibrium conditions, and Q, our reaction quotient, is for any other conditions that are not necessarily equilibrium. So let's look at a situation where we increase the volume of the solution by a factor of 2. So we're doubling the volume. That means we're going to half the concentration. So now let's write down half the concentration of our product, and we'd also have to write down half the concentration of our hexa aqua cobalt complex, and also half the concentration of our chloride ions here because of this doubling in the volume. Okay, now we can see that these two are probably going to cancel out fairly easily. And if we're going to take this out the front, what we're going to have to do is apply our factor of 4 there, our power of 4. And when we go 1/2 to the power of 4, that's right, saying 1/16. And if we put 1/16 out here, what's going to happen is we're dividing 1 divided by 1 on 16 is going to turn out to be 16 out the front here. So now let's actually try and compare our reaction quotient to our equilibrium constant. So we can see that this is exactly the same as our equilibrium constant out the front. This part doesn't change, but we have this power of 16 out the front here. So to achieve dynamic equilibrium, what we need is our Q to go back to our K. So we need to reduce the size of this Q, and the only way we can do that is by increasing the concentrations down the bottom here, and that will make this number here smaller and make our Q equivalent to our K. So in other words, if we were to double the volume of the reaction, that means we're going to halve the concentrations and our reaction will proceed towards the left here minimizing the concentration of our tetrachloro complex. So our blue color will dissipate and we will get more of a red color. So this follows Le Châtelier's principle, and Le Châtelier's principle states that when a system in a state of dynamic equilibrium is acted upon by some stress, for example, a change in concentration, pressure, or temperature, the equilibrium will change to minimize the effect of this stress. So if we have a look at this reaction again, what will happen if we increase the concentration of these chloride ions? And if we have a look up in the top right-hand corner, you can see me adding sodium chloride to the solution. Now sodium chloride will ionize to give us sodium ions plus chloride ions, and it's these chloride ions that are going to have an influence. And we can see that the reaction turns to a blue color from the purplish color of the equilibrium before. Okay, so that follows. This increases, the reaction proceeds to minimize this increased concentration. And now when we add our water here, if you look up in the right-hand corner again, we're going to decrease all of these concentrations here. But because this power of 4 has the greatest effect, our reaction will proceed towards the left-hand side of the reaction. Here's our purplish pink complex that we made before from adding our cobalt chloride to our hydrochloric acid. And remember, it's purplish pink because we have this mixture of the hexaaqua complex and the blue tetrachlorocobaltate ion. Now, we can actually change the position of this reaction by changing the temperature. So I'm just going to dip it into this water here, which is at around about 70 degrees Celsius. And we can see that it's slightly changing color before our eyes, going to a more purplish blue color. And hopefully we can change it all the way to a blue color. Here we are, here's the blue color, almost. Here's our endpoint, which is our blue complex, which is our tetrachlorocobaltate ion. Now we can change that back to our hexaaqua complex just by cooling a solution, and I'm just dunking here into ice water. Ice water is of course at 0 degrees Celsius. So you can see that as the solution cools down, it changes back to this purpley red color, and then finally it'll turn to our pink color. And we can see that it takes longer to actually cool a solution than it does for the reaction to actually occur. But you can see I can change which side of the reaction the reaction proceeds to just by changing the temperature of the reaction. And we can understand this through equilibrium, understanding equilibrium, and understanding the Le Châtelier's principle. And here's our pink color here. We can use Le Châtelier's principle to predict which direction a reaction is going to proceed in when we heat or cool it. To do that, we need to actually look at its enthalpy, and the reaction that we had here, the hexaaqua cobalt ion going to tetrachlorocobaltate ion, is an endothermic reaction, meaning it takes energy to do the reaction. So because it takes energy to do the reaction, we can think about this reaction as adding heat over to the reactant side. We've got to increase the amount of energy in the system to get the reaction to proceed. So when we do that, we can then see that if we increase the amount of energy in the system, then the reaction will proceed in a direction to minimize that change. So we will get our blue tetrachlorocobaltate ion, which is what we saw in the video before. When we decrease the amount of heat, our reaction will proceed in a direction to minimize that change. It will try and produce more heat. What we've got to realize in this situation, however, is that we're not just influencing the position of the equilibrium, we're actually changing the equilibrium constant, because the reaction rate constant for the forwards and the back reaction is going to change according to the Arrhenius equation.